All right. HDMI to the rescue. Well, it's good to be here, and thanks so much for being patient and for actually staying for the very last session of the day. And in this presentation, I want to talk about self-play. It's one of my favorite topics. I think there are deep connections to meta-learning, and now self-play has also been a lot on our minds after the recent AlphaGo Zero results with chess. And so, before we begin diving into the technical content, I just want to remind you a little bit about what it is that you're trying to do with OpenAI. We want to build AGI, we want to solve the alignment problem, and also one way to articulate it is solve the ownership problem. We want the benefits to be widely distributed and an arms race of AGI to be avoided. So now, let's begin with a review. Oh. All this, this is some online learning we have right here in real time. So, is this, let's see. Let's try this. So, I want to mention old work in self-play, and that is T.D. Gammon. It's 1992, so this is prehistoric ancient history. And what's really amazing about this work is that it's just so modern. It's basically could have been written in 2017 just with much, much slower computers. And you can see the plots. They show the performance of their system when their neural net has 10 hidden neurons, hidden units, 20 hidden units, all the way up to 80. And they've used Q-learning to train the policy, train with self-play, and to be the world champion. And so, the foresight is just amazing. But this just gives you kind of the first instance that I'm aware of where self-play did something really, really cool. So, later on, I think we've all seen AlphaGo Zero, which showed that you can do self-play to defeat the strongest humans in Go. You can do big, large-scale self-play with the right self-improvement algorithm. And if you do that right, then you also can beat all humans in Go, and not just in backgammon. So, it means that self-play can work, at least in principle. And it makes sense. Just play against a system which is a clone of yourself, roughly the same level, and it just keeps getting better as you're getting better. Another result of self-play was our very own result in Dota 2, where we defeated the world champion in the 1v1 version of this game. And this was also a pure self-play result. And by the way, so the Dota game, not everyone here may know what it is exactly, but it is the biggest competitive esport game, and it has a very large, serious professional scene, and over $100 million in prizes were awarded to champions last year. And so 5v5 is the main challenge, and we've solved 1v1. But again, self-play really does work. So that's encouraging. It's encouraging for self-play. But why should we be excited about self-play? Do we just want to solve games? Games aren't real life. What can self-play do for us that's better than this? So, I think that the promise of self-play at the core is that it gives you a way of creating really complicated challenging for your agents out of a very simple environment. So fundamentally, in a self-play settings, you have a simple environment, and you have simple agents which are powered by powerful neural networks, powerful learning algorithms. As the algorithms learn, the environment becomes more complex. And it just feels like a very natural place in which you might want to train your ultimate meta-learner, because the agents will create lots of difficult challenges for each other. One other thing that is very nice about self-play, which is not particularly deep, but it's still nice, is that you have a perfect curriculum. So when your agents aren't very good, then your opponent isn't very good. So you still win about half the time. But then as you get better, your opponent gets better. So it's always challenging. If it's set up just right, it may be possible to just allow this self-improvement process to go on indefinitely. So one really cool place where this was explored was in artificial life. So artificial life was something which is a little bit like deep learning in the sense that it was tried in the past and then it didn't work, so everyone gave up on it. And this is like, I think, the coolest work on this kind, which was done by Carl Seens. There is a really cool YouTube video if you just Google Carl Seens artificial life on YouTube. Like what they've produced, they've evolved a whole bunch of really cool morphologies of agents doing really complicated things, and it's just amazing that we're able to do that all in '94. But people tried it, and it didn't work. So of course it doesn't work. Well, no, of course the computers were too slow. So one thing that we were motivated at OpenAI was to see if we can apply self-play to something else, which is not just a game. Oops. Yeah. So here, like, we have a simple environment. You have this disk, and you just want to stay inside the disk. It's sumo. You just want to push the opponent out. That's all the information that the agents have. And just from this information, just look at what they figured out. Look at this. And this, we injected a very small amount of information into the system. It's just that when the opponent gets good, you need to get good. And so you generate this rich and complex strategy. But then you don't just want complexity for free. What you really want, this is cool, you should see this. So this is not exactly symmetric self-play, but it is still the case that as the red agent becomes better at kicking, the green agent needs to get better at blocking. Now, of course, all of this is small. Oh, this is cool too. So you see here, so the green agent was able to dodge under the arm of the red agent. So their balance is pretty good. And here you see we do a very, very simple transfer learning where we say, okay, let's take the sumo agent and just apply random big forces on it and see if it can maintain its balance. And here it is, maintaining its balance, even when you apply forces on it. And so you can see what the promise is here, that if you create a bigger and better multi-agent environment with more agents with conflicting goals, they will create their agent society. And they'll develop social skills and theory of mind. And so one of the big challenges with this line of work is to find a way so that the agents that you train with self-play are useful for an external task. And I think this is the very important research question that needs to be addressed. So the kind of thing we were thinking about with those wrestling humanoids was that, okay, so they're going to be good at wrestling, and then perhaps it will be very easy to fine-tune it to maybe cook a simulated egg. If it's good at wrestling, it's good at cooking a simulated egg as well. But I think this is an important part of this research. The self-play, you can see that it can produce a lot of different challenging tasks for agents, which is what you need for meta-learning as well. Meta-learning thrives when there is a great variety of tasks, and this setup can produce it. But it is also important to do the final step of actually taking these agents outside the simulation and getting them to do things which are truly useful. And right now, the next step in this line of work is to do that, to demonstrate that it is possible to take the agent out of the simulation and get it to do something that is very difficult to achieve by any other means. I also want to highlight one very important characteristic of self-play systems. So self-play systems have a property that if you set them up exactly right, you will experience a very rapid increase in the competence of these systems. And this graph right here shows the true skill, which is essentially the ELO rating of our Dota bot as a function of months. So in April it was pretty, Oh, now this thing at the bottom is not going to go away. Oh, yeah, great. So in April, it was totally bad. And then, we scaled it up a little bit, fixed some bugs. It became a little better in May. And then by late May, it was pretty good. Then in June, it beat an amateur. In July, it beat a semi-pro. And in late July, it was kind of a pretty strong pro, but it wasn't the best. So you just scale up more, fix more bugs, and you see like it's the end, it's just the scaling up. It just keeps getting better and better and better and better. And it's clear why. Because in self-play systems, you can convert compute into data. This is one of the very attractive things about it. In normal supervised learning, you're fundamentally limited by your data set. Your data set creates an insurmountable ceiling of how far you can go. But in self-play, if you want more better results, you just put more better compute, and your results get better. Now, I want to now present a hypothesis. The hypothesis is that, at least in principle, the AGI systems, there's a good chance that they will be trained via this kind of self-play. And I want to give some speculative evidence for why it might be so. So one thing that we know from biological evolution is that social animals tend to have larger brains. There exists at least one paper from Science which supports this view. One thing we know about our own evolution is that we've experienced an intelligence explosion on a biological timescale, where the volume of our brains have tripled in size over the past 2 million years. And there's it's definitely a neat hypothesis to say that it happened because we were living in these social tribes, and we got so good at surviving that suddenly our social standing in the tribe and what other agents think of, what other prehistoric humans think of us, is the most important thing. And so you can clearly see how such open-ended multi-agent systems could produce theory of mind, negotiation, social skills, empathy, and maybe even real language understanding. But that will require some effort. And I want to finish with a speculative slide. So if you accept the claim that multi-agent systems, once done right, experience a very rapid increase in performance, and you accept the hypothesis that the first AGIs will be built in such competitive multi-agent systems will self-play, then we should also see a very rapid increase in the competence of our early AGIs. And this concludes my presentation.
Ilya, a very nice presentation, and I fully subscribe to the idea that for true open-ended AI, having the environment evolve as part of the training is probably necessary. Now, there's a rich and long history in the field of co-evolution, which can, so self-play can be seen as the most simple form of co-evolution, where the environment varies during training, right? And one of the big problems in co-evolution that was found was that it's hard to get the evaluation diverse enough and not to focus on very specific tests or opponents. Is that something that you encounter? Because I'm surprised that by self-play you don't encounter the same problem.
Yeah, so I think maintaining, so the question of how do you avoid a collapse of your behaviors into very narrow, low entropy subspaces. And this is definitely a practical problem that we saw even in the Dota system. And it feels a lot like neural net training, where it's something that happens, but if you add a lot of variety to the environment, if you randomize, if you add various, all kinds of dimensions of variability to the environment, we've observed that it makes the problem diminish a lot. And so I think that it will be important to keep adding this variability, having not just one opponent, but multiple opponents, and basically having multiple types of opponents. I think these kind of approaches will be essential to make this robust and stable.
Okay, makes a lot of sense. Thanks.
Hi. Very nice talk. Thank you very much. But I was curious. I love seeing your presentation of the Dota bot, but to the best of my knowledge, you haven't actually published anything about it. Is there any time frame where we could see something on archive at the very beginning?
Yeah, so right now we are working on the 5.5 version, and I hope that in not too far in the future, it's all going to be out there.
Okay, that's good, but it would be nice to see, like, this is a contribution that I think the community would like to see, and I'm just surprised that something like this, where it's been presented and been blogged about, hasn't had a submission for basic methods.
Yeah, I mean, I think like this definitely makes sense, but the way we would like to do it is we want to finish the 5v5 variant first.
Okay, I had this saying, like, comparing to AlphaGo 0 and TD Gamma, and it was kind of an outlier that these are like large-scale milestones, but one has nothing publicly available.
Well, the milestone is still work in progress.
Okay, all right, very well.
So it's obvious that the singularity weighs heavily on your mind, but you admit that 20 years ago we just didn't have the computing power to do what we're able to do now. So do you have an estimate of how much computing power we might need to get to that singularity ramp?
Well, I think you can definitely make, so I wouldn't want to use that term. I think it has lots of connotation, but I think you can definitely make arguments as to how much compute is needed. Like, if you can run brain scale models much faster than real time, you're probably okay.
But can we do that?
Well, not today, obviously.
So, well, Moore's law is ending, so how much silicon square meters are we going to need for this?
I mean, for sure it's going to be a large computer. But it's like, okay, so that's a great question. So I think when people were looking at the feasibility of putting objects into space, one of the counter arguments that were used is that you're going to need something like 500 tons worth of fuel into the rocket. There is no way it could happen. Well, what happened? The rockets just ended up being really huge. And I agree that it's going to be a big operation. It's not something small, but these things are possible.
What happened is that we're not in space.
Well, so it is true that we are not in space, but the reason for that is that they haven't finished the job. Their rockets would be destroyed every time they were used. If the rockets somehow were reusable.
Hi, I'm Ernest Young. Thank you for the talk first. My question is, can you give more color about when you said more compute equals more, and I forgot the right-hand side, but give more color about more compute. Is it either you want more parameters in the model to make like the number of weights bigger, or is it just optimizing the mathematical operations so they run faster?
I mean, at the basic level, all it means is that in a self-play system, if you got more compute, like the self-play system, at its core, allows you to convert compute into data. So what it means is that if you have a lot of compute, your agents are going to get a lot of experience, and you'll have a lot more to learn from. That's basically all it means. So if you have more compute, you have more experience, you have more learning.
Yes, I'm sorry, we've got to stop there, but there'll be a panel discussion, and we'll reconvene in 1 hour's time for the final session. Let's thank our speaker again.